Let's see this question. Construct the minimal finite automata that accepts all strings over the alphabet A, B, where length of each string is divisible by 3. So the length of the string W is congruent to 0 mod 3, right? So when we divide the length of the string with 3, it leaves a remainder 0. So the possible lengths of each string are 0, 3, 6, 9, 12, and so on. All these are multiples of 3s. Multiples of 3, right? Each string should be either length of 0 or 3 or 6 and so on. By looking at this, we'll have epsilon in our language, right? Because the length of epsilon is 0, which is congruent to 0 mod 3, right? So let's see what are all the strings we have in this language. Epsilon, AAA, AAB, ABA, ABB, and so on, BBB. All these are of length 3. Similarly, we will have strings of length 6 also, like AA, so on till BBBB, BB. All these are of length 6. We will have strings of length 9 and strings of length 10, strings of length 12, and so on, right? We have seen similar question earlier where we constructed DFA for strings having number of A's congruent to 2 mod 3, similar to this, right? So there we had a constraint over A. There we had the number of A's should be congruent to some R mod n. Here we have constraint over the string itself. We don't care about the symbol, right? So in the similar lines, here we have 0 mod 3. So the reminders, the possible reminders when we divide a number with 3 are 0, 1, 2. Therefore, our states will be Q0, Q1 and Q2. Since we concentrate on remainder 0, our Q0 will be our final state, right? And as usual, Q0 is always our initial state. So the DFA looks like Q0 is our initial state and final state, because we are concerned only about 0, the remainder 0, and Q1, Q2. These are our states in our DFA. On seeing any symbol, it can be either A or B, we move to Q1 from Q0. And on seeing any symbol from Q1, we move to Q2. On seeing any symbol from Q2, we move to Q0. So this is our DFA. We don't have a constraint over the number of A's or number of B's. We just have a constraint over the length of the string. So all these strings which are of length 3 and all these strings which are of length 6 and so on are in this language. The strings like AA, BA, these are not in our language because the length of the string is 4 when we and it is not congruent to 0 mod 3. It gives remainder 1 when we divide 4 by 3. So this is not in our language, right? Let's look at this. Here the length of the string is congruent to 2 mod 6. We need to construct a DFA, minimal DFA, for all the strings having length congruent to 2 mod 6. Our alphabet is A, B, right? Since we have mod 6 here, we will have Q0, Q1, Q2, Q3, Q4, Q5 as our states. And since 2 is the reminder, we will have q2 as our final state. This is our final state, and q0 is our initial state. So the DFA for this will be q0, q1, q2, q3, q4, q5, and q2 is our final state and q0 is our initial state. On seeing any symbol from q0, we move to the next state q1. On seeing any symbol from q1, we move to q2. On seeing any symbol AB, we move to q3. From q2, similarly same happens at q4 and q5. On seeing any symbol from q5, we move to q0. This is our minimal DFA for strings having length 2 mod 6, length congruent to 2 mod 6. So from the previous examples, we can see that number of states in a minimal finite automata that accepts all strings of length congruent to R mod n has exactly n states. So whenever you are asked a question like number of states in a minimal finite automata where each string is of length R mod n, you can blindly say that there are n states and the final state will be QR. Starting from q0, we will have q0, q1 and so on qn, and qr will be one of these states. So qr will be our final state and there are n states in such a minimal finite automata.